Left brain is the brain that's called the interpreter. That's the brain that does math. That's the brain that thinks, comes up with words, breaks the world into little cubes, which is nice for doing math. And your right brain is the one that handles everything else. That's the ambient brain. So your left brain is spotlight brain. I'm focused. Right brain is floodlight brain. It's everything else. It's the space where things happen. So we just fall back into that for a moment. And sometimes we forget stuff because we're so into our right brain. Am I recording?
Yeah.
Oh, good. Okay, cool. Thank you. I appreciate your IT support. All right. Well, let's do a quick little review. Here's a particle in motion. I've got position at time t, time, and let's say this is in meters. And again, this stands for position. What I'd like you to do is, I'm going to give you a graph, and I'd like you to come up with the movie for the particle. So remember how the other day, just a quick refresher, if I walked across this way and I sped up as I ran this way, and I'm the particle, my motion would look something like this. Slow, 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 faster, faster, faster. The distance covered in the same amount of time increases as I move to the right because I'm speeding up. What is this particle doing? So just maybe on your picture or in your brain, come up with a picture for this guy right here. Let's say that's 10 seconds. That's 5 seconds right there in the middle. And these are like the 2.5 and then 7.5 seconds. What's a particle doing? So just think about it and then we'll talk about it. But interpreting these graphs is a key part of what we do in here. I'm gonna put my microphone on. Forgot about it. I'm not used to this protocol. What you thinking? Are you thinking? You're still thinking? Okay. Yeah.
You're relatively at the same pace, and then you're slowing down, and then you're speeding up, and then it's like the
Yeah, but when you're saying something about it going reverse, you said that's negative, so
Yeah.
that's like backward.
Yeah.
You think, that's good. Yeah. I think we got all that on here. What you thinking? Okay, cool. Okay. Well, let's start. So here, let me give a little. Here's an extra anchor in case it would help you with your storytelling. Let's say that's 3 meters right there. So I'm starting. If 0 is the left side of the board, I'm actually starting about 3 meters out this way. What is my distance doing, or my position? What happens as I move time forward? So I'm at 3 feet, decreasing. So which way am I moving? So I'm right here. I'm at 3 feet. Which way am I moving toward? Because think of this. Here's 0 right here, this little line. Here's 3 feet right here, this little mark. Where am I moving toward? What position? What's the height? Here I'm at 3. A little later, where am I at? How many? I'm less and less and less. I'm moving toward the 0 position. So this is this 0, is this guy right here. So I'm moving backwards. Then what happens? I'm right here. Now what do I do? Do I move forward, or am I moving even further in the other direction? Is S positive or negative here? Negative, right? So which side? So here's the positive stuff. Which side of 0 am I on? So I'm moving that way. That's kind of how to think about this. Sorry to put you in. You weren't really on the spot, but I just, yeah. Can somebody tell us a story about movement here? What are we doing? Anybody? Joshua. Moving back and forth. So I put a little 3 here. This is where we're starting, at 3 meters away from the 0 position. So I'm going to say the 0 position is this line right here. So I start at 3 meters. As time moves forward, my position decreases. So I'm actually moving back towards 0. I'm moving backwards. Let's see if we can see that with the idea of average velocity. So let's look at my average velocity over this first 2.5 seconds. So remember, notation is AV, 0 to 2.5. What is that? Can you compute that really quickly? You can use the graph. We should be able to actually do that one. What is that actual exact value? So we're reviewing some of the stuff we talked about, and were you in a calc class and transferred in? Okay. That's good. No, that's good. We're thinking. We're racking our brains. How's it going? Thinking. Fantastic. Thinking. Oh, that's so beautiful. Can I write what you wrote up here? Okay. Here's a good first move. It's the position at the end of the interval minus the position at the beginning of the interval over the change in this interval. So over 2.5 minus 0. And we are using the formula AV of T0 to T1 is my position at the end minus my position at the beginning over the change in time. That's the formula we want to use. On upcoming homework, which will be coming up soon, I'll give you one next Wednesday, we're going to be using this all the time, and we're going to get really in there. So can someone else help me out? What's S of 2.5? Yeah, 0. Yeah, we good? We do LC 0 right here? The output is 0. Beautiful. So 0. What's S at 0? 3. Awesome. We can do this. We can do this. We got this. And then the bottom's just going to be good old 2.5. Yeah, exactly. Negative 3 over 2.5, and that's like a weird number. We get our calculator out. It's like approximately negative 1 point something here. What is a negative velocity? Backwards. So this just says, since this is negative, a negative average velocity means we moved backwards. And a positive would mean we move forwards. What is a 0 average velocity? Didn't do really, you're back where you started. You might have actually even moved. You might have moved, but your average velocity is 0. You haven't gained anything. You haven't really accomplished much. If moving is your thing you're trying to accomplish, bless you. Is there a question? Can I answer any questions on what we've done, just to make sure everybody's with me? A little bit of review. All right, let me make this problem a little bit more interesting. What if I said S of t is cosine of t. Why would I say, why am I moving there? Can someone tell me, what do you think my thought process is here, Sam? Yeah. Looks freaking like a cosine, right? Hey, could you practice for the quiz and make a cosine graph for me? Just one period from 0 to 2 pi. We talked about this a lot last time. There actually is a recording up of the first 45 minutes of class on my YouTube channel, but I'll tell you all that afterwards. So I record every class. So at least you can kind of like go back and catch the first intro part. And this will actually effectively review this part for you. So, yeah. Oh, we do have everybody. I don't know why I thought there's someone else in here. And heck, if you get done, why don't you just like quickly test yourself on this one? Get that out. We'll put the answers up and then we'll compare notes. See how yours turn out. Maybe you can even grade mine for me. Let me know if I'm doing it right. Start with the same box for both of them, right? Make ourselves a nice little frame. We try to help ourselves in life, right? Just try to make life easier, plan out our routes. Seen some nice graphs. That was so good. Very good. These are looking good. Some of you are getting crazy, even doing more than a period's worth. Beautiful. Oh, that was good. Oh, I like how you fixed that. Yeah. Looking a little sharp. It looks beautiful. So it is. So on this part, think concave down. You know what I'm saying? Yeah, a little softer. Yeah, just like that. Perfect. Lovely. Little more concave, just a little. See, like that guy, little more concavity, just right there. But otherwise, beautiful. That's the right rhythm. We're looking for the rhythm. Oh, look at that. Oh yeah. Okay, I won't look. All right. So cosine starts at its high point. Halfway through, it's at its low point, and then it's back to the beginning. And I'm essentially going to put dots in a V shape. And everybody got that. But be careful. We don't want this thing to look sharp like that. We're looking for, it's kind of flat right there, and then it comes down. It's about a 45-degree angle as it crosses the axis. In fact, it's exactly. And then down here, you hit the bottom and softly bounce back up. And it's kind of looking shitty because I'm trying to stretch and draw. So if you'd drawn this, I probably would have said, you could do better. I could do better. I was just stretching. But your graph should look essentially like this. And one of the things I saw several folks doing, there we go, that's a little better, is we want this concave down and concave up. So opening down on the ends, opening up in the middle. It looks like an upside down bell curve. Yeah, actually, yeah, totally. If we think about what a bell curve looks like, it's upside down bell curve. So if that makes sense and helps you, that's, yeah, very nice. And then sine starts in the middle, ends at the middle, hits the middle in the middle. High point, a quarter of the way, low point, 3/4 of the way. And then again, I want that beautiful smoothness to my curve. So now let's answer some questions. Oh, no question, just a cough. Cool. So let's work with this. Forget about that for the moment. Could you please find the average velocity on 0 to 3 pi over 2? And then I'm going to give you another one. So what is that? And then please find this. The first one, you can use your picture. Second one, you're going to have to extrapolate some information. We're limbering up for calculus. Sophie. Okay, cool. Just checking. Awesome. I lost my seating chart already because that's the way I roll. So those two graphs are going to be on the quiz next week. Next Friday, we'll have a little quiz. So I'll pick a problem or two off the online homework we're going to set you up with, and then I'm going to ask you to reproduce those graphs. Yeah, so you're halfway there. We're almost there. You already knocked this out. Yeah, I'm going to have to make stuff harder for you, I guess. Quite nice. Oh, you're going crazy. I like it. You're getting the job done. Asha's bravely producing many periods of this graph, and that's a great way to do it. Do what you got to do. Make a little move there. If that move is unclear, ask me about it, please. And I would gladly explain. You can ask me about anything, and should, if you find yourself wondering what just happened in here. Oh, how do we feel on that first one? We all good on that? Do you see the move I made? Did everybody get to here? How about that? We're at -1 over 3 pi over 2. Do you see the move I made to make here? Do you want me to explain it? Some good, some good? Anyone need that move? I multiplied the top and bottom of this fraction by 2 to clear out the little fraction in the bottom. So the 2 comes on top. This is the reciprocal of 3 pi over 2. Looks like that. So we see we've got a negative velocity there. Addie, you did this one. How did you come up with s at 10 pi? Cool. So let's check that out. Looking for those rhythms. So we can take this graph and reproduce it. Probably 5 more times we'd have to reproduce it to get these numbers. But we can look for these rhythms that sine is 1 at even multiples of pi. So out here again at 4 pi, it's going to be back at 1. Out here again at 6 pi, it's going to be back at 1. So I know that at 10 pi, it's 1. Those even multiples. So this is going to be 1 minus, and then using a similar, in between these guys, you have your odd multiples where it's minus 1. There's 5 pi right in the middle. It's minus 1. So this S of 7 pi, I'm at an odd multiple of pi, so I'm right at the trough. I'm in the middle of the trough. So I've got to be careful. Look, I'm doing a minus. The value of this is negative 1. So I'm going to put it in parentheses and be careful. Use parentheses, please. Use as many parentheses as you can. And then the bottom is just how many pi's? 3 pi's. There's 10 of them, minus 7 of them. There's 3 of them left. The top becomes 2 over 3 pi. And damn, that's beautiful. Like, I didn't know it would turn out so cool, but it kind of did. So that's like, oh, nice. A little gift from past me to present me, that they're just the same number, but minus and negative, or minus and positive. Questions, friends? Cool. Let's push this forward just a little bit. Could you sketch that out for me? And let's say that t can be any number. So t is any number on the real line. So that's greater than negative infinity and less than positive infinity. What's the graph of the position function? And right now I'm just seeing if you know what e to the t looks like. And if you don't, that's okay too, because we're about to talk about it. If you got that one, you might suspect what's next. Could you do this one? And I'm going to ask you, what value of t makes sense here? So I'm good. We're upping it up just a little bit worse, deeper. So it's like, the little frog in the hot pan. Just cranking up the heat a little bit. I don't like that because I love frogs, and I'm not mean to any little critters. Frogs are amazing, yeah. No, I'm vegan. I don't like mess with any. Are you? Nice. Maybe we could share some recipes. I try not to be one of those people who says I'm vegan a lot. I know that people have issues with vegans and vegetarians and stuff. What does that mean? What is a vegan vegan? Oh. Yeah, I like that. Cool. And that's what I was doing, right? Okay, cool. All right, good. I just want to make sure I'm in the good boat. Yeah, happened a long time ago. That's a story for probably not class. Come by my office, we'll talk. Let me see how this is going. Can I take a look? Yeah, kind of. Kind of. Yeah. We got any? No, we got no E's. Got no. Oh, okay, cool. A stumper. Okay, that's a good start. Yes, as long as we have axes drawn, we've already really, really close. Oh, yeah, so right. Okay, you got there's the feel is there, and that's pretty. It's close. It's a little pointy right there. It's an ouch. I wouldn't hurt myself on it. Let's just talk about this. So, what is E? It's a what? Euler number? Yeah, it's a number. So this, I love it. That's Euler's number. Euler was one of the great mathematicians of all time, like mathematics god. We're, as mathematicians, he's like a demigod to us. Quite amazing mind. What is it, though? Whoa, yeah, you're making me very happy. 2.71-ish. I like it. So 2.7, 1828, 1828. If you say that, you'll have more digits than anyone will ever want. But look how nice it is. 2.7, 1828, 1828, and then a bunch more. Keeps on going. But damn, there's 9 digits, 10 digits of E right there in front of us. Good stuff. So it's like a little less than 3. And that's a good thing to keep in mind, just for like estimating and understanding what's happening. It's like 3-ish, it's under 3. But as long as you know that, you know more about Euler's number than most people. So this number is like 3 raised to various powers, roughly. Think about what happens if I take 3 and I raise it to higher and higher powers. This probably is hard on your brain, but I bet this is less hard. So like when t is 1, the output's 3. When t is 2, the output's what? 9. And then when t is 3, what's the output? 27. So it's really shooting up. What happens when t is 0? Yes. So let's get the low-hanging fruit. Any number. So if you have a non-zero number and you raise it to the power 0, that is equal to 1. Just a quick reminder, any number raised to 0 is 1, except for 0. That's weird. We don't talk about this. Don't think about that. That's actually a weird thing that you'll learn more about as you progress in calculus. So S of 0 is 1. There's an anchor point right now. And Joshua had that anchor point. But you didn't have that anchor point. But it's okay. You have, then the shape then to the right, it just blows up. This is exponential growth. The E, exponential growth. What happens as I move to the left? So in other words, at -1, what is S of -1? And we can maybe approximate it. Like, what's it approximately? Well, first off, let's plug it in, right? Just plugging it into the formula. Yeah, now we, so I wanted to talk. It's not that, though. What does this mean? 1 over E. And what is that approximately? 1 what? What is E approximately? 3? It's like a third, right? So it's like a third. So when I move to the left here, this is down. It's actually gone down. It's like, approximately a third. It's actually a little more than a third, but it's good enough. What happens when I've got S of -2? Can you take a second? Come up with a ballpark estimate for S of -2. Don't say it out loud. If E is approximately 3, what is E to the -2? Remembering that a negative exponent is a reciprocal. It flips things and then uses the power. Oh, this is fun. This is good. Yes, that looks good on your left. Your left, I'm just like very excited about how that left side looks and working here. Josh didn't want me to see. Very obviously blocking my view. What is it? What'd you say? I thought you said something.
I'm talking myself.
Okay, cool. What do you think it is, Sophia? Oh, no. So it's going to be E to the -2. How do I rewrite that without a negative exponent? 1 over E squared. So when you have something raised to a negative power, So here's something. It's 1 over that thing to the positive power. This means reciprocal. Flip. Does that make sense? So you flip it, then do the power. It happens in the bottom of the fraction as opposed to the top. So this right here translates to this. Now, Sophia, what is it approximately? If e is approximately 3. Yes, ma'am. Yes, beautiful. It's like a ninth. It's a little more than a ninth, but it's like a ninth. So that means it actually trimmed down by another third of where it was here, so it's getting closer. And then it just keeps shrinking more and more. And, oh, geez, I'm Joshua in that thing there. It's giving you a hard time, Fred. Just in a loving way. I'm going to move my one to fix it so I don't have a little sharp spot there. So it keeps getting closer and closer. What do you call that kind of behavior when you get closer and closer to a line? What was it? Say that word again. Indicate. Decay. Thank you. Sorry. Decay. Yeah, there's decay, definitely. So I'm seeing some decay. What do you call the graph behavior when you are approaching a line like this or like this? So like, I'm thinking of a math, that's true, not in a physics way, but what do you call those? Oh, that's too, that we're not there yet. That's later. You're right. Yes. Approaches 0. Ooh, nice. It's good. Thinking same thing. Let's play hangman. Oh, yes, that's the word. Okay, asymptote. So this is asymptotic. Asymptotic. It's hard to know what I was looking for, Joshua. I appreciate it. You're right. It is decay. But this is asymptotic behavior. This just keeps blowing up. This is exponential growth. This is asymptotic decay. Let's use that nice word that Joshua tossed in there. It's quite beautiful. Okay, so if I ever said to you, hey, we've got this function, f of x is e to the x, you have in your brain this picture here. Well, that's okay. I'm roaching it up. That's asymptotic. They don't touch. Just pretend they don't touch. That's what E looks like. And the key thing is, where does this cross? How high is that? 1. Have that little graph. Throughout this course, I would make like a little chart that I just had in my notes that I could look at these until I know them well. Because you really are going to want to know what E to the x looks like. What the hell is that? Anyone care? Yes. Leo.
It's, I don't know how to describe it, like that.
It is like that. How do you read this? When you look at this statement up here, how do you read this in your brain?
Yes. The inverse of log. Natural log.
It's the inverse of the exponential, but it is the natural log. Yes, perfect. So this is equal to the natural log. I think it's good we're taking this time to talk about all this stuff. The natural logarithm of t. You can also write it like this. This is the logarithm base e of t. We just have a special symbol for this. I think we better talk about logarithms. Because I got a feeling we need to. Let's talk about how you understand what this is. Because most people don't have a good understanding. So here's a quick little digression. Logarithms. If I say to you y equals b to the x, I have this statement here. This number is this other number raised to this power. Logarithm is just a different way to say the same thing. So this is the same as x, what is it? Yeah? Yeah, what is it? Oh, it's okay. I like that you were jumping. You're like so stoked to say it. Say it. Okay, all right, you chickened out. Come on. Yes, sir.
Is it y sub b equals x?
Log of. So you got you're seeing it in your head. I see you seeing it, but it's actually like this: that the exponent I have to raise b to get the number y is x. I would write this down. So the logarithm, this thing here, this is the exponent we raise b to. This b is called the base to get y. So let's actually play with this a little bit. If I asked you, what is the log base 3 of 3? Can you come up with that using that idea? Let me give you a couple. Oh, just hold it. Yeah, do you think you got it? What do you got? Show me. Yeah. Yes. I'm going to give you a couple. I have to go pee. Sorry, I didn't tell you that. But I'm going to put a couple problems on the board, like I'm throwing like barrels in front of you to keep you from getting me in a pursuit. So I'm going to give you a few things. Find these, please. And I'm going to give you 2 more. And then 1 more. Oh, hell, 2 more. That's a 1. Please find these. This is a good practice. I'll be right back. Maybe if I can even find my way around here. I just realized I had this mic on. I'm going to have to edit the video before I post it. Not great. Hopefully the connection doesn't reach out that far. Good, we're still thinking. Excellent. Remember to read it as what power do I have to raise 3 to get the number that's the bigger number? I'll start going through, giving you answers. How do we feel about 1 on that first one? What power do you have to raise 3 to get 3? 1. What power do you have to raise 3 to get a third? -1. Beautiful. What about a 9th? -2. And we did that earlier, right? We actually did that just a little bit earlier. So hitting back on that. What power do I raise to get -3? So what power, I like this is good. This was a trick one. You jumped in on the trick one. That's awesome. What power gives me a negative out? No power. Can't answer, but I love that you went for it. Yes, thank you. Like day one, you're like getting in there, wrestling with it. This is undefined because there's no power, no real power I can raise 3 to get a negative number. That's a trick one, so good work. What power do I raise 3 to get 1? Yeah. Yes, cool. Yes, 0. Yes, you got, 0. Awesome. The graph for log, so let's go back really quick. Let's review this or talk about this. If I have y equals e to the x, and I'm flipping variables intentionally, here's my graph of y equals e to the x. Really the key point to remember is that intercept. This is the inverse of e to the x. It is the inverse function of e to the x. It undoes e to the x. And we'll talk about that in a minute. But you can get the graph by flipping this graph over the diagonal. So if you want to remember what natural log looks like, take e to the x, which you know, and flip it over the diagonal. Now think about how that works. You're going to imagine in your mind folding this over, creasing it, and you're going to see something like this. And that is my graph of natural log. What is this point right here? That is 1. Because what power do I have to raise e to get 1? 0. So the graph of natural log looks like this. It is not defined for negative x. There's nothing over here. So it's undefined when x is less than or equal to 0. And you have this asymptote. This asymptote here becomes that vertical asymptote over there. And this is a 1. All you need to remember is that detail, and you've got the flow. This is going to pay off. I know you're like, what is he making us do all this? It'll pay. This is going to pay off. Yes, sir.
For natural logs, instead of using parentheses around x, use absolute value, right?
We can, definitely. And I think you're thinking of derivative formulas. And definitely, at some point, we will have natural log of absolute value of x. If I did have this, it now allows x to take a negative value because I'm going to strip it away with the absolute value. So if I asked you to sketch this graph out, it would actually be just the normal natural log graph doubled up on itself. So you'd have this positive version and this negative version. Does that make sense? Yeah? Cool. Good thinking. Yeah. Any questions on this at all, friends? All right. We've got some time. We've got a good bit of time. I want to push this into the calculus realm. Because that's kind of the end of we'll always be reviewing the whole semester. We're going to review the whole semester. I'm going to actually improve your ability to sketch sine and cosine at some point, but I think today there's more important things to talk about. Let's look at a very specific distance function. So I'm making the move into studying what is called instantaneous velocity. We've already talked about average velocity, which is over an interval, but we're going to move to the calculus realm with this. So this is moving towards calculus, and if you, in particular, a thing called limits, which will be one of the first things we talk about, calculus-wise. So S of t is 4 minus t squared over 2 minus t. Let's just come up with this simple. Now we're back, right? No trig, no logs. Everybody's happier. This is like polynomials and stuff. It's like chill. What would be a terrible value for t to be? 2. Why is that? 0 in the bottom. We don't want to divide by 0. So we would have to say over here, s should not equal 2 because we don't want to divide by 0. So we don't want a 0 in the bottom. That's bad news. Let's find a few things here. What is, using that s, the average velocity of on 1 to, well, let's start off chiller, 0 to h. H is, I don't know. H is a thing that'll change. What is this? You'll have a formula that'll depend on h here. Oh, here we go. Now we got some work to do. Just go with the formula, step by step. So what I'm trying to encourage you to do here is to just use the definition of average velocity, plug in the values, first write this. I'm going to encourage you more and more to use notation to keep your brain safe. That's technology. It offloads it from your brain. So write, take steps. There's nothing gained by being super fast at doing these things. You don't get extra points. I'm going to make a sketch of this thing while you work on that. Get some different color in here today. Oh, actually, let's have Desmos do something for us too. Oh, come on. All right, screw you, Regis. Good, that's on the recording. It won't let me log in, so we won't use Desmos. I'll make my graph anyway. I'm going to get a graph by just plugging in some numbers and taking a look at what comes out. Oh wait, did I put in a 2. How did I do that? Well, because I lied. I can't put in a 2. Can't do it directly. I'm just cheating. I was doing a limit in my head. That's bad boy. There's an open circle right there. Let's do one more. -2. I put in -2. I get a 0 on top before in the bottom, so I get out a 0. So if you've sketched it all out, if you've got a graphing app or your calculator, and if you want to bring graphing calculators to class, because that helps, do so, please. Or you get the Desmos app for your phone. It's pretty awesome. It's free. Don't need to buy anything. But got that. Let's start taking a look here. So when I plug in the H, so that's the S of H. When I plug in the 0, I get 2. And when I just take this bottom, I get H. Did we get to here? We're there? Okay, cool. Did anyone make any cool moves from here? What cool moves did you make? Because there are cool moves to be made. I like it. Okay, so look at this move. There's a little fraction and a bigger fraction. And this will be the second time we've seen this move today. I'm going to multiply through by the little fractions denominator to clear out the little fractions. So what I'm going to do is I'm going to multiply the top by 2 minus h, and I'm going to multiply the bottom by 2 minus h. And let's do that to simplify this. So on top, 2 minus h times this guy, that cancels. And I'm left with 4 minus h squared. And then minus 2, this 2 gets times that, so minus 2 times 2 minus h over, now the bottom, I'm just going to leave like this. And let me stop, and you tell me if that looks okay. And Kyla, is that kind of looking like, yeah, okay, cool. How do we feel about that move? And if it's unclear, let me know. I'll happily explain it. If it's unclear to you, you're not the only one. And I could, if I put this in parentheses, that maybe that'll make it feel a little bit better. Okay, you got to tell me. I'm going to trust that you're not, that when you say nothing, it's because you're just about there or you have processed it. Get in the habit of not being afraid to say you don't get it. That's what we're here for. Nobody knows calculus well enough yet to not be in this class. So I'm going to simplify that. That is 4 minus h squared minus, now I'm going to distribute, minus 2 times 2 is minus 4. Minus 2 times minus h is plus 2h. And then the bottom is just, I'm going to leave the bottom factored for a minute. Yes?
Why can't you cancel out the 2 minus h from the tops and the bottom?
Thank you for asking that, because I was thinking, I wonder if anyone's thinking about doing that. So let's talk about that. You mean these guys right here? Yeah. So if you canceled those, you got to be careful. You can only let's talk about canceling. If I have fractions and I have something like this, like a plus or a minus on top, and then I have something else at the bottom, and these two pieces look the same, I can't cancel from a sum. What I can only cancel from, so this is no good, but I can cancel from a product of things. That I can do. Would you remind me of your name again, please? Sorry. Sabrina, thanks, Sabrina. So if this had a parenthesis like this, then I would have 2 minus h times this whole thing over here, and then they would cancel. But unfortunately, this piece doesn't have that 2 minus h on it. Does that make sense? So that's why I'm not canceling yet. You can only cancel from a product when you have a fraction. Yeah? Does that help a little bit? Okay. So that's great. I was hoping that question would get asked because that's a common mistake. So now come up here. I'm going to simplify a little bit more. Anything nice happen on top? Yeah, right? Bye-bye. Cool. Starting to feel, all right, nice. That always feels good when stuff starts to come apart. So let's rewrite. Rewrite slowly. Now, Sabrina, eventually it is going to cancel, but it can't be seen right there. So you maybe deep inside, you're like seeing a little bit further ahead. Let's move with that. We'll go with that. But we have to do the work to get there first. Can someone help us make another move? Yes.
And the denominator you distribute.
I would leave. So what I'm kind of hoping is that something will cancel. And I'm going to leave that bottom as a product, so maybe something cool like this will happen.
Okay.
Does that make sense?
Or you could take an H out from the numerator.
There, that's a better move. Is that what we were going to say? Yes. Pull factor. So when you've got a fraction, factor and hope for cancellation. So absolutely. I'm going to pull an H out of the top. So I've got H times what's left over. Well, a minus H, because that times that is that, plus 2. And then in the bottom, we've got H over 2 minus H. Yes?
You might also want to pull it everyone.
Ooh, I like that. So what do you think? Oh, because right, because these kind of look the same. But how about this? We actually could just flip the order of these two and make that 2 minus H. Because I think that's what you're wanting to see, right? If I pull out a minus, I guess, well, I think this might be a better move for us, like that. But you're thinking the right way. How does this look? Whoa, what's going on? H can be any real number. Provided H isn't 2. Because otherwise I'd have 0 here. But look how these things cancel when I get there. I ended up with 1. What? Wait a minute. This looks terrible. The average velocity, no matter what H is 1. Does that make sense? It kind of, look at the picture. It does. Look at the picture. This picture, if you plot out this graph, what you'll see is that it's a straight line. And there's an open circle right at 2 because I can't let it be exactly 2, but it's a straight line everywhere else. What's the slope of this line? It is 1. Every one you go over, you go up 1. This is saying that the average velocity, let's think about what the average velocity, from 0, so here we're at 0, to an arbitrary H, so I move out H units here. So this distance right here, this is the change in the position. This is the change in the input. And no matter what that triangle looks like, the slope of it is always 1. No matter how much this is, the ratio of this to this is constant because the slope is 1. And that's all we've seen there. We saw it algebraically. I could see it with the picture right over here. And if I could pull up freaking Desmos, I could show you with Desmos. How does that stuff feel? Okay, let me ask you another one. So now you saw that one. Could you please do me a favor? Let's see. What is the favor I would like you to do? What time are we at? How about we call a little early today, because I need to talk to a few people about web work. Does that sound okay? No one has a problem with that. So let's call it a little early today. And if you have not done web work, if you haven't logged in, maybe you could do it on your phone right now. Let's knock some stuff out. If you have, bye, you're good. Or hang out and talk to me, or whatever you want to do.
Funny thing I said distribute the H through on the denominator,
Yeah.
it worked out just fine.
Oh, it does. You can see it.
worked
You're
out-
right.
It worked out just
Yeah,
fine.
that's
why-
cool.
That's why I said that.
It's beautiful. Yeah, you're right. In general, though, just be careful. Yeah. But you're right. It did work out really nicely there. Yeah. Hi.
I just have a question. So I did log in. I just didn't,
Oh.
like, how do I do this?
Oh, okay, cool. Okay,
I was just
this is great.
curious.
Oh, okay, great. And everybody will get full credit for this logging in as long as you do it by the end of the day. There's no problem. So bye, thank you. So you just click on the homework set and then you come in here and oops, I'm doing some kind of stuff. But here you go.
Just
And,
answer a question.
and just
Oh,
try
okay.
it. Here, let's do it. That's all I
Okay.
wanted. Now you're
Oh.
done. Complete.
All right. Thank you.
Good stuff. Thanks for staying. Fixing it up. Hi.
I still have to do the web work.
Okay.
But I also have to do a placement test that I have to get done. So
Go take care of it.
Yeah.
But do it by tonight.
Gotcha.
Okay. And if you have any trouble, just email me and we'll figure it out.
Thank you.
Okay. Thanks.
The world.
Oh,
right, yeah.
gotcha. Yeah, we got it. Bye. Thank you. Bye. Thank you. Can you pull up world class?
Yeah.
Yeah. So let's go to our class page.
Let's see here.
Let me go stop the recording.
Yeah.
Nobody needs to see this.